Tonight, you and I are going to explore a reality that feels like science fiction but is the most brutal physical truth I know. Deep space. It is the void beyond our planet's tiny protective bubble. You have seen the movies' heroes drifting through stars and building colonies on alien worlds. But those movies lie to you. Stepping into that vacuum involves a horror that almost everyone out there completely misunderstands. By the end of our journey tonight, you will see why the void is not just dangerous, it is a predator that attacks every biological system I rely on. Before we head out, if you love exploring these dark depths as much as I do, take a second to like the video or subscribe. It is a small thing, but it helps us reach more curious minds. Now, let us begin with something you already understand. Survival. You know what it takes to survive back home. You need air, water, food, and a world that stays at a predictable temperature. Your body evolved to expect constant protection from the elements. Back on Earth, that safety is provided to you automatically. The atmosphere gives us exactly 21% oxygen. The temperature stays in that perfect zone where liquid water can actually exist. Gravity anchors us. The magnetic field acts as a shield, deflecting lethal radiation. Ozone blocks the ultraviolet light that would kill us. It all happens effortlessly. This is the baseline your biology assumes will always be there. Now imagine I start stripping those protections away one by one. That is the terrifying reality of deep space. It takes every single thing I need to survive and deletes it instantly. Out here, the void is actively trying to kill me. Let us start with the first thing I worry about: pressure. Or rather, the terrifying and complete lack of it. Right now, wherever you are feeling atmospheric pressure, about 14.7 pounds per square inch, or 101,000 pascals. That is the weight of miles of air pressing down. You do not feel it because it pushes equally from every single direction. We evolved to thrive under this weight. Imagine that every square inch of your skin is feeling nearly 15 pounds of constant pressure. Your entire surface area, about 20 square feet, is actually enduring about 43,000 pounds of total crushing force. That is over 20 tons of force. It does not crush you because the pressure inside your own body is pushing back out. Your blood, your organs, and your lungs are perfectly synced with the air around you. It is a state of balanced equilibrium. This balance is so vital to survival that nearly every biological process I have depends on it to function. My heart pumps blood through vessels at pressures carefully tuned to the weight of the air outside. Your lungs need pressure gradients to move air. Even your cells maintain an internal balance that assumes the Earth is pushing back. I am a biological machine calibrated for exactly 1 atmosphere. If I lose that, my body breaks down with catastrophic speed. My lungs only work because of these pressure differences. When I inhale, my chest expands to lower the internal pressure. Air rushes in to equalize things. When I exhale, I compress my chest, creating a higher internal pressure that forces air out. This entire process needs that baseline pressure. My blood, my fluids, and the gases in my tissues must stay in sync with the atmosphere. Now imagine the nightmare when that atmospheric pressure vanishes instantly and completely. This is vacuum exposure. The effects hit me in less than 1 second. It starts with something called ebullition. Gas bubbles start forming in my fluids. Under normal pressure, oxygen, nitrogen, and carbon dioxide stay dissolved in my blood and tissues. Pressure keeps them trapped in solution. Think of it like a sealed soda bottle keeping the fizz inside the liquid. Think about when you crack that seal. That hiss is carbon dioxide escaping, forming those bubbles that rush to the surface. You reduce the pressure by removing the cap. Inside my body, there are gases dissolved in every fluid I have. Nitrogen makes up 78% of what I breathe. It is currently dissolved in my blood and my tissues. Oxygen dissolves too, though hemoglobin carries the bulk of it. Carbon dioxide, the waste product of my metabolism, stays dissolved in my blood. These gases are in total equilibrium. If I lose that pressure, just like opening a soda, those gases instantly tear out of solution. They form bubbles everywhere. Unlike soda, these bubbles are not harmless. They form deep inside my circulatory system, my tissues, and my vital organs. They cause immediate, agonizing damage. The moment I lose pressure, the gases in my body just explode out of solution. Bubbles form in my blood, my saliva, even the fluid around my eyes. The medical term is decompression sickness, though you likely know it as the bends. Divers get a mild version if they surface too fast, but what I face in the vacuum of space is infinitely more severe. This is not a slow change. It is an instantaneous, violent drop from one full atmosphere down to essentially zero. Bubbles erupt everywhere at once. My blood begins to foam. My tissues swell as the gas inside me expands. The water in my mouth and lungs begins to boil not from heat, but from the lack of pressure. This is vapor pressure boiling. Water boils at 212 degrees Fahrenheit at sea level. But in this vacuum, water boils at lower temperatures until it happens at body heat. Looking down at Everest from here, I know the pressure is so low, water boils at just 154 degrees Fahrenheit. Up here in the vacuum, water boils at body temperature. That is 98.6 degrees. Imagine your saliva boiling right on your tongue. I have seen the data eye moisture boils away. Lung fluids bubble and froth. It sounds like a horror movie, but it is just raw physics. This is what happens to any liquid out here. We understand the science, but that does not make it any less terrifying to think about. You see, boiling points depend on the vapor pressure molecules need to break free from their liquid state and escape into the void. With high external pressure, molecules need massive energy or high heat just to push back and escape into the atmosphere surrounding them. Lower that pressure, and escape gets easier. In this vacuum, molecules can break free at almost any temperature above absolute zero. My body stays at 98.6 degrees Fahrenheit. Out here, that is incredibly hot compared to the void's absolute zero. That heat is enough to turn me into vapor. My mouth, throat, lungs and eyes would literally start boiling in this silent void. It is not like a stovetop. It is a rapid, ghostly evaporation. Flash boiling that just vanishes into the stars. We have seen it happen. We do not use people for these tests, obviously. But water in our vacuum chambers reacts the same. It boils instantly at room temperature. My own blood obeys these laws. Now, here is something you and I should consider about the nature of space itself. The vacuum isn't just one thing. It changes depending on where I am. Believe it or not, space is not totally empty. Even out in the deep dark, there are a few atoms per cubic centimeter. It sounds like a whole lot of nothing. Compared to Earth's thick atmosphere, which has 10 to the 19th power molecules per cubic centimeter, it really is effectively nothing. But it is not absolute zero pressure. It is just so close that, for us floating out here, the difference does not really matter. Down in low Earth orbit, where I'm stationed on the ISS, there is actually a bit more matter floating around. Our atmosphere reaches up hundreds of miles, thinning as it goes. At my altitude, 250 miles up, stray air molecules still linger. These particles create drag on us. We gradually lose altitude, so we need engine boosts to fight orbital decay and stay in the sky. Without those boosts, we would spiral down and burn up. Yet, even here, pressure is just 1/1,000,000th of what you feel at sea level. For me, it is a total vacuum. Getting caught outside without a suit would trigger all those horrific effects I have been mentioning. Further out, past our atmosphere, the density plummets. In deep space, you might find only one lonely atom per cubic centimeter. That is as close to a perfect void as nature allows. That is the emptiness we would face on a journey to the stars. A pure, nearly perfect vacuum. No protection from the cosmic radiation out here. Meanwhile, the very air inside my lungs would start expanding. My lungs hold about 6 liters of air. In this vacuum, that air wants to expand and fill the entire infinite universe. If I held my breath out here, my lungs would rupture instantly. That expanding air would tear my delicate tissues apart. It is why divers learn never to hold their breath while rising. Even 10 meters of pressure change is enough to be deadly. Going from 1 atmosphere to 0 is infinitely worse. Even if I exhale instantly, I am only buying myself a few extra seconds of life. That is because the damage from embolism is already taking hold. But that is just the start. We have to talk about oxygen. My brain eats up 20% of my oxygen, even though it is only 2% of my total body weight. It is a hungry organ, always processing data, keeping me conscious, and making sure the systems keeping me alive stay running. Without oxygen, my brain cells die in seconds. On Earth, I could hold my breath for a minute before blacking out. But that is with oxygenated blood. Out here, my lungs would be empty. The expanding gases would have forced everything out. My blood would start foaming from embolism. It could not carry oxygen even if I had any left to give it. I would lose consciousness in 10 to 15 seconds. That is all the time my brain has to use up the remaining blood oxygen. After that, I am out. Brain damage starts in minutes, and I would be completely brain dead in 4 to 6 minutes. But I would not even last that long. While my brain shuts down, other catastrophic failures would be happening all at once. Those gas bubbles forming in my blood, they would cause massive circulatory chaos. My heart would still try to pump through my veins, but that blood is now full of bubbles. Those gas pockets create blockages, stopping my lifeblood from flowing where it needs to. My tissues would be starved of oxygen and nutrients even faster than if I had just stopped breathing normally. My heart might start pumping foam instead of liquid blood. Even if you pulled me back inside now, the damage would be catastrophic. The bubbles, the tissue damage, and the lack of air all collide. Some have actually survived brief vacuum exposure in accidents. We have records from the 1960s where suit failures exposed my predecessors to the vacuum for a few seconds. They lived because they were repressurized instantly, but they said they could feel the saliva boiling right off their tongues. They even described the sensation of their skin swelling up. I have seen it happen. They black out in seconds, 10 to 15 seconds, that is all. Longer exposure is a death sentence. But we are just getting started. Pressure and oxygen are only the beginning. Now, consider the cold. Everyone knows space is freezing, but you and I should look closer at that. People imagine absolute zero, which is minus 459.67 degrees on the Fahrenheit scale, or minus 273.15 degrees Celsius. But reality out here is a bit different. Space does not really have a temperature. Remember, temperature is just a measure of how fast molecules move. In this vacuum, molecules are rare. What you actually feel is the touch of thermal radiation. Anything above absolute zero bleeds radiation. The hotter it gets, the shorter and more intense the waves become. Hot objects glow with visible light. Cooler ones emit invisible infrared radiation. Even the void has a pulse. We call it the cosmic microwave background, a ghostly, ancient radiation. It is the universe's leftover heat sitting at minus 454.75 degrees Fahrenheit, or minus 270.42 degrees Celsius, just barely above absolute zero. Floating out here, far from any sun, you would be wrapped in this faint chill of minus 270.42 degrees. That sounds like a quick death. But here is the secret. You would not freeze instantly. Forget the movies. You do not turn into ice in seconds. Heat transfer in a vacuum follows its own haunting, difficult rules. On Earth, you lose heat through contact, air, or radiation. Conduction and convection keep things moving down there. Up here, there is nothing to touch. No air to carry your warmth away. Those rules just vanish. There is nothing to steal your heat. Your only way to cool is through radiation. At 98.6 degrees Fahrenheit, or 37 degrees Celsius, your body is slowly leaking infrared into the dark. Without a sun to warm you, you would eventually cool down, but it would take hours, not minutes. The lack of pressure and oxygen would end your story long before the cold ever set in. Still, if you had oxygen and a pressurized suit without insulation, the freeze would eventually find you. It is a slow, creeping frost. Your fingers go numb first, then the chill migrates deep into your core. Your internal systems would just shut down. Hypothermia takes your mind, then the dark takes the rest. But again, that takes hours. The image of a flash-frozen astronaut is pure Hollywood myth and nothing more. Then there is the fire. Close to a star, you are being shredded by a storm of intense radiation. The sun is a furnace. Near Earth, it hits you with 1,361 watts per square meter. We call that the solar constant. Half your body would be drinking in that lethal energy. The other half faces the abyss. Without air to move heat around, you are being torn apart. Your sunny side would literally boil. Your shadow side would sink into the deep, dark freeze of the void. That temperature split would be agonizing if you were awake, but honestly, you would have drifted off long before that point. Vacuum exposure kills fast. But those thermal extremes are just the beginning of the nightmare out here. Now, we have to talk about radiation. Back home, the atmosphere and magnetic field are your silent guardians. Out here, you are hit by solar particles and cosmic rays, high-speed bullets from the farthest reaches of space. Most of this never reaches Earth's surface. The air and the planet's core shield you from the worst. The magnetic field deflects the danger, turning deadly particles into those beautiful auroras that dance across the polar skies. You are protected without even knowing it. Let us look at the different types of radiation I see every day. Solar radiation covers everything: radio waves, microwaves, infrared, and the much deadlier X-rays and gamma rays. Most of this screams through the vacuum, just invisible energy traveling at the speed of light. Visible light reaches us, obviously. It is why we have vision, plants, and power for our ships. Infrared heat makes it through too. That is how the sun keeps your world alive. But the high-energy stuff, ultraviolet, X-rays, and gamma rays, is mostly filtered by the air you breathe. The ozone layer catches the worst ultraviolet rays. What slips through is just enough to give you a tan, but the truly lethal UVC is completely blocked. Out here, there is no shield. That radiation shreds your DNA, causing mutations that lead to cancer. It is a silent, invisible killer. Out here, if my skin caught the full UV spectrum, I would have severe burns in minutes. It is not heat. It is radiation shredding my cells. My skin would redden, blister, and basically start falling apart. And that is just UV. Next come the X-rays and gamma rays, the invisible killers I cannot even see. Solar flares and mass ejections scream across the void. High-energy photons that can punch through almost anything. Back home, the atmosphere swallows them up. Up here, they pass through the hull like it is not there. One intense solar flare could irradiate me in an instant if I was not tucked behind some heavy shielding. This radiation pierces my tissue, damaging every cell in my body. But honestly, solar flares are not even the worst threat. The real nightmares are galactic cosmic rays. Atomic nuclei, stripped naked and accelerated to mind, bending, terrifying energy levels. They come from the deep dark supernovas, neutron stars, and black holes. Violent cosmic events from beyond our system. When a star dies in a supernova, it dumps more energy in seconds than our sun will in its entire lifetime. That explosion hurls particles out at nearly the speed of light. They are screaming across the galaxy in every direction, mostly protons, but also heavy iron, carbon, and oxygen. These tiny bullets have been traveling for millions of years. Eventually, they reach us. Luckily for you, Earth's magnetic field deflects most of them before they hit home. Your atmosphere absorbs the rest. You are safe. But for me, I have no protection from these single atomic nuclei. Moving at 90% of light speed, they carry kinetic energy millions of times higher than anything in a lab. When one hits my body, it does not just damage one cell. It sets off a cascade of secondary shrapnel. It rips electrons away, creating a path of chemical chaos. It can literally shatter the DNA molecules inside me. It can kill a cell instantly or mutate it, planting the seeds for cancer to grow later on. These energies are massive compared to my biology. But one hit will not end me, not yet, anyway. You are being hit right now too. Even on Earth, some make it through. We are all constantly under fire. Most zip through harmlessly. If they cause damage, my body tries to repair it. That is our built-in defense. But out here, the dose is the poison. Back home, maybe a few rays hit every square centimeter each second. Most do not leave a mark. Your lifetime risk of cancer from cosmic rays on Earth is basically nothing. Up here, the flux is relentless. I am taking hundreds or thousands of hits per square centimeter every single second. It shifts with solar activity. Without Earth's magnetic shield and thick air, I am standing right in the firing line. Over time, the hits add up. Every collision is a gamble with cancer. More hits simply mean worse odds. Even with the station's shielding, my radiation dose is about 150 to 200 times higher than yours. 6 months on board raises my lifetime cancer risk by 1%. That does not sound like a lot, right? But that is 1% on top of everything else. For a young astronaut like me, that is a heavy price. And that is just low orbit. Once we leave Earth's magnetic field for deep space, the environment gets much deadlier. NASA has estimated that a round trip to Mars would hike our cancer risk by about 5%. That is right on the edge of what is acceptable for us volunteers. But let us be honest, it is not safe. And Mars is close. A mission further out would take years. More time in deep space means more radiation poisoning. We are talking cataracts, heart damage, and effects on the central nervous system. Cancer is not the only monster here. There is evidence this radiation eats at your mind. Animal studies show cosmic rays can actually change brain structure. That means memory loss, trouble solving problems, and crushing anxiety. My very personality could start to unravel. We are still studying if this happens to humans, but for a long-duration mission, it is a terrifying possibility. We cannot have crew members losing their minds on a multi-year trip. We need to stay sharp to survive. If we cannot think straight during an emergency, the mission is over. Shielding helps, but it is just not enough. You would think thick walls would help, but cosmic rays are so fast they punch through meters of solid material. We cannot carry that much weight. Every kilogram we launch costs a fortune in fuel. Mass is our biggest enemy. There is a limit to what we can bring. My ship's aluminum hull is only a few millimeters thick. It stops some solar particles, sure, but these cosmic rays, they punch through like the hull is made of paper. We could use water tanks. Water is actually better than metal because it does not create as much secondary shrapnel. When a ray hits aluminum, it shatters the metal's nuclei, creating a shower of secondary particles. Hydrogen-rich materials like water absorb that energy without making things worse. But I would need meters of water to really stay safe. That is thousands of kilograms of extra mass. It is nearly impossible to launch and even harder to manage in zero gravity. Every designer faces this impossible trade-off. More shielding adds mass and cost to my ship, but less means we get cooked by radiation. Our current designs accept some exposure as a given, trying to keep us safe within tight limits. We plan our deep space missions around these invisible killers, timing launches for the solar minimum. Activity is lower then. Still, we have to build storm shelters into the heart of our craft. It is where we hide when things get ugly. Keeping our missions short helps limit the total damage. You cannot outrun the risk entirely. The void is radioactive, flooded with high-energy particles. Stay out here long enough and you will get hit. Every hour in deep space adds up fast. It is not something I can just engineer away. We can slow it down, but never stop it. Without a suit, the dose I would take is massive, though it won't make me sick immediately. Before the vacuum kills me, radiation sickness needs hours of exposure to really take hold of my body. Even if I survived the pressure and lack of oxygen, the radiation would destroy me within weeks. Out here, there is no shield. It hits you directly. Solar rays pack enough ultraviolet light to fry skin. Cancer follows soon after. Without our atmosphere to filter it, the UV exposure is absolutely brutal. But UV is the least of my worries. The real killer out here is ionizing radiation. These are particles screaming through the void at near light speed. Cosmic rays are basically flying atomic nuclei, protons and helium mostly, born from supernovas and accelerated to energies that defy our imagination. They carry millions of times more energy than anything we can generate in our labs back on Earth. When they strike my body, they rip through my cells and shred my DNA, leaving destruction behind. The damage is instant, and it builds up. A single ray can punch through several cells at once. Every strike is a gamble with mutation. Over time, the internal damage just keeps mounting up. Up on the station, we take doses 150 to 200 times higher than you do. Earth's magnetic field still guards us somewhat, but even with that, we are getting hit hard. 6 months out past the magnetosphere, and my cancer risk starts climbing in a very real way. On the long haul to Mars, we would soak up enough radiation to change our health outlook forever. With the tech we have now, there is no perfect shield. These particles are too powerful to stop. Thick walls help, but they are too heavy for our ships. Sometimes, the wrong shielding makes it worse. Secondary radiation bursts when rays hit the hull. It is a constant threat for us inside the craft. If I stepped out without a suit, I would be flooded with radiation long before I actually died. It is enough to ensure total system failure. Even if the pressure did not kill me, rays would. It burns my tissue and shuts down my organs. Then there are those terrifying solar particle events. Every so often, the sun screams, releasing massive bursts of charged particles during intense solar flares. These storms can hit us with enough radiation to cause acute sickness in just a few hours. Getting caught in that without a suit is game over. Even inside my ship, it is incredibly dangerous. We watch the sun constantly. Back during Apollo, those guys were truly vulnerable once they left Earth behind. They got lucky. One big flare at the wrong time, and those crews would have been lost forever. As we plan for Mars, we cannot ignore this. Our ships must have dedicated radiation shelters. These are the safe zones where we retreat. But out in the open, there is no survival. Let's take a closer look at what happens to my body during that first minute. Let's trace it. 0 seconds. The exposure starts. My environment drops from a full atmosphere to a cold, dead vacuum. 1 second. The air in my lungs expands. If I try to hold it, my lungs will tear. The air rushes out. The spit on my tongue starts to boil. My eyes feel the moisture vanish. 2 seconds. Ebullition sets in. Bubbles start forming in my blood and deep inside my own tissue. My skin swells as gases expand underneath. Within 4 seconds, the boiling water vapor freezes my mouth. My nose feels a flash of cold as I bloat up. 6 seconds in, and my circulation fails. Those bubbles block my blood flow. At 8 seconds, my brain is starving for the last of my oxygen. Out here, once your lungs empty, it is over. 10 seconds later, your brain oxygen drops so low, you simply black out. Your vision tunnels. Sounds fade. By 12 seconds, you have drifted into darkness. You are unconscious now, blissfully unaware of the horror. 10 seconds later, your heart keeps hammering, pumping blood that is fizzing with deadly bubbles. Without oxygen, your brain begins to shut down. Within 30 seconds, your entire body starts swelling up aggressively. You would look bloated if anyone could see you. Your blood pressure swings wildly as your circulation fails. 1 minute in. The damage to your brain becomes permanent. Even if we pulled you in now, you would never be the same. By 90 seconds, your heart is giving up. Your heart might flutter weakly, but your brain is gone. 2 minutes out here means clinical death. No pulse, no thoughts, no coming back. That is the reality of the deep space vacuum. If it is only a partial vacuum or a quick rescue, you might survive with fewer permanent scars. We know of people who survived brief brushes with the void. Back in 1965, a technician was testing a suit at Johnson Space Center. His suit failed inside a vacuum chamber. He faced the void for 14 seconds before they could pump the air back in. He described feeling the saliva on his tongue boiling. Then he just blacked out. Once the air returned, he woke up and eventually fully recovered. 14 seconds seems to be our absolute limit for survival. But that was with doctors and air right there. Out in the deep black, there is no rescue coming for us. There are no walls to hold the air. Just infinite vacuum. Without a ship or a suit, you are not surviving. Period. Now, let us look at what happens to a body left out here for the long haul. If you were to pass away and be left out here, what would happen? On Earth, your body decomposes through several natural processes. Bacteria and insects usually handle the job of recycling your tissues back into the earth. Oxidation and moisture fuel decay. But out here, none of that works. There are no bacteria in this vacuum and no insects. But you still have bacteria in your gut. After death, they would keep breaking down your tissue for a while, producing gases. Without atmospheric pressure to contain them, those gases would simply leak out into the void. You would dry out completely through sublimation. That is when solids turn straight into gas, skipping the liquid part entirely. In a vacuum, ice sublimates. The frozen water in your tissues would slowly vanish, leaving behind a freeze-dried husk of a body. If you drifted into the sun, one side of you would cook, possibly rotting from the intense heat. Your shadow side would stay frozen. Far from any star, you would become a permanent ice sculpture in the dark. Temperature extremes and radiation would slowly shred your organic molecules. UV rays from nearby stars would cause chemical changes in your tissue. Cosmic rays would continue to hit and damage your molecular structure. Over millions of years, you would slowly break down into atoms. In the short term, over decades, a body in space would stay mostly intact, frozen and dried out, but still recognizable. It sounds grim, I know, but it shows you just how alien our environment is compared to Earth. The rules of life and death we grew up with do not apply once you leave the atmosphere. Let us talk about the engineering required to keep us alive out here, because the technology is absolutely mind-blowing. We survive thanks to high-tech gear and constant focus. My spacesuit is basically a tiny, wearable spacecraft. It gives me everything I need to stay alive, especially pressure. These suits keep us at about 4.3 pounds per square inch. That is the standard for NASA. It is thin air, but it keeps our blood from boiling so we can breathe. Thinner pressure makes the suit easier to move in, but go too low, and there simply is not enough oxygen to keep you conscious. It is all about partial pressure. In Earth's atmosphere, the oxygen you breathe makes up only about 21% of the air. At sea level, that provides about 3 pounds of oxygen pressure. Our lungs need at least 2.5 pounds of oxygen to function. If you drop below that, you develop oxygen starvation. That is why we use pure oxygen in a suit at 4.3 psi. No nitrogen, just pure oxygen. This keeps our life support systems simple and the suit flexible enough for us to move and work. But this creates other dangers. Pure oxygen is a massive fire hazard. A single spark can ignite materials that would never burn in normal air. This was tragically proven during the Apollo 1 fire in 1967. 3 fellow astronauts were conducting a test inside their module on the pad. Their cabin was filled with pure oxygen at 16 pounds per square inch higher than normal air. A single spark hit the oxygen and the entire cabin exploded into a wall of flame instantly. The cabin filled with smoke and fire in seconds. They could not escape because the hatch design required the pressure to be equalized first. Today, you and I remember the 3 who choked on smoke before the hatch opened. Virgil Grissom, Edward White, and Roger Chaffee. Pro-pilots and engineers gone in 60 seconds because of a fire that would not have been half as lethal in normal air. That disaster changed everything. Now, we use fire-resistant materials and new hatches designed for a fast escape. Pure oxygen is a bomb waiting for a spark. My suit mitigates that risk by keeping the internal pressure low. At 4.3 ps1, things catch fire less easily than at 16. Still, I have to be careful. No open flames. I am constantly scanning for sparks or heat. Why? Because inside this suit, there is absolutely no escape. If a fire starts in here, I am dead instantly. That is why oxygen management is so critical. My life depends on fresh oxygen and scrubbing carbon dioxide. My tanks release compressed O2 at a steady, controlled rate. I breathe the good stuff and exhale the poison. Without the scrubbers, carbon dioxide would kill me in minutes. My suit uses lithium hydroxide canisters. They react with my breath, pulling the carbon dioxide right out of the air. It is a simple chemical reaction. Lithium hydroxide plus carbon dioxide creates lithium carbonate and water. The gas turns into a solid compound, keeping the air clean. But these canisters have a very strict limit. Once they are full, they just stop working. If that happens, I am in serious trouble unless I replace them. For a typical 6 to 8 hour spacewalk, I carry enough to keep the air safe with a little extra margin. You and I have to remember, if the mission drags on or I get stuck, my scrubbing time starts ticking away. Carbon dioxide would rise. I would feel dizzy, then confused, until I finally blacked out and drifted away. We almost lost people during early missions when things took too long. Now, we build in much more safety margin. Bigger canisters and backup systems are standard now. But the fundamental danger? It never truly goes away. My suit can only keep me alive for so long. Then there is the heat, a massive, invisible threat. Out here, heat does not just drift away, it can only radiate. Meanwhile, my own body is constantly generating warmth. I am pumping out 100 watts just resting. When I am working, it is even worse. That heat has nowhere to go. Without cooling, I would bake in minutes. Heat stroke would set in before I even knew I was in danger. I wear a liquid cooling garment against my skin. Think of it as high-tech underwear woven with tiny tubes. Chilled water flows through those tubes, pulling the heat off my body and carrying it back to my life support pack. From there, the heat is bled off into the void. It is a complex dance of pumps and pressure. Massive heat exchangers and sensors are my lifeline. They have to work perfectly to keep me from boiling alive. If my cooling fails, I have maybe 10 or 15 minutes before the internal temperature becomes fatal. We have seen these systems fail before. Usually, the astronaut catches it and rushes back to the safety of the airlock. I can switch to backup, but it is another single point of failure. If it breaks, the consequences are final. Then there is the sun. Without an atmosphere to shield me, the solar radiation out here is absolutely brutal. The solar constant is roughly 1,360 watts per square meter. That is a lot of raw energy. That equals about 1.8 horsepower hitting every meter of my suit. I can feel the energy soaking in. My outer layer is a bright, reflective white to bounce that light away, but some of that heat still bleeds through. The temperature difference between my sunlit side and my shadow side can be hundreds of degrees. It is surreal. In the light, it is 250 degrees Fahrenheit. In the dark, minus 100 degrees Celsius. My suit has to handle that massive gradient. Heavy insulation keeps that outer heat from reaching my skin. The system balances my body heat against the sun's fury. It is a delicate, dangerous game of thermodynamics. It has to adjust constantly, whether I am working hard in the sun or resting in the freezing shadows. All that engineering is packed into this wearable suit. But pressurized fabric naturally wants to become a rigid sphere. A sphere is impossible to work in. I need joints points where I can actually bend and move. Shoulders, elbows, wrists, every single pivot point has to bend while keeping that precious internal pressure sealed tight. We use complex bearings and fabric tricks to make it work. But even the best joints feel incredibly stiff. Every movement is a fight against the pressure. Bending my elbow is not just a motion, it is a physical struggle. Imagine trying to bend a partially inflated truck tire. That is what every movement feels like in this suit. You and I might see the grace of a spacewalk, but it is grueling work. 6 hours out here is more exhausting than any terrestrial job, especially with these stiff gloves making control a nightmare. Up here, I am constantly fighting my own gear. Turning a simple bolt feels like wrestling a stiff, pressurized balloon. Every grip is a battle against the suit's internal pressure. After hours out here, my hands just quit. Cramping, aching, total exhaustion. I have seen colleagues lose entire fingernails just from the brutal, relentless pressure inside those rigid gloves. My nails could literally lift away from the bed. It is agonizing. Better tech helps, but the fundamental danger never leaves. A pressurized glove is a stubborn enemy. It resists every twitch. There is only so much engineering can actually fix. Our current suits are engineering miracles, sure, but they are also massive, insanely expensive, and need constant babysitting to stay functional. These suits cost millions of dollars each. They weigh 280 pounds on Earth. Up here, weight doesn't matter, but mass and inertia are absolutely lethal. Shifting that much mass takes real muscle. Stopping is even harder. Momentum wants to hurl me into the void long after I stop pushing. These suits aren't exactly new. Most of what I am wearing was built back in the 1980s or 90s. We swap parts and upgrade systems, but the core design is decades old. NASA is working on new suits with better mobility and smarter tech. We are testing advanced materials, but building a new suit is a slow, incredibly expensive drain on resources and time. It takes years of brutal testing and certification to ensure every single system survives the worst-case scenarios out here. Engineers have to eliminate every single point of failure that could potentially kill me while I am working. The complexity is staggering, far beyond what most people realize. My suit isn't just a protective shell, it's a complete life support system in a wearable package. Pressure, oxygen, cooling, power, everything has to sync up flawlessly. If one gear slips, my entire world falls apart. Everything has to fit into a suit I can wear and move in. One tiny seal leak or a single pump breakdown puts me in immediate, life-threatening danger. That is the reality of my job. Even with the best tech, it is risky. We plan every single spacewalk down to the second. I practice every move. Every tool is triple-checked. We have backup plans for every nightmare scenario you can imagine. Redundancy is everything, but things still go sideways. Leaks, cooling failures, or a sudden tear in a glove happen despite our best efforts. Usually we catch them before they turn fatal, but the threat is always hovering. Out here, space does not forgive a single mistake. There are no second chances. One major failure, and I have minutes, maybe seconds, to crawl back to the safety of the airlock. Oxygen is life. My suit constantly feeds me air while scrubbing out the carbon dioxide I exhale with specialized lithium hydroxide canisters. Temperature control is critical. This suit has to constantly pump out the intense heat my own body generates in this vacuum. In the direct sun, I am shielded by reflective layers. When I hit the shadow, heavy insulation keeps me from freezing solid. I wear a liquid cooling garment that circulates water to chill my skin. As for radiation, the suit offers some protection, but not enough. It blocks some radiation, but cosmic rays still pierce right through. We schedule our spacewalks to minimize exposure and avoid sudden solar particle bursts. Mobility is the ultimate goal. I need to be able to move, work, and handle tools without fighting the suit's rigid shell. It is harder than it looks because internal pressure wants to turn me into a stiff, human-shaped balloon. The joints fight that. Gloves are the worst because I need precision. All this tech is packed into a suit that weighs 280 pounds back home. Weight isn't the problem up here, it is the mass and inertia. Even so, this modern suit is an absolute marvel of engineering, but it is also bulky, restrictive, and terrifyingly expensive. Every single suit costs the program millions of dollars. They need massive maintenance. I only have 6 to 8 hours of life support per walk, and trust me, they are not perfect. Suit failures happen. I have heard of leaks, cooling meltdowns, fogged visors, and shredded gloves occurring more than we would like. Usually, we make it back before things get fatal, but there have been some chillingly close calls out in the void. In 2013, Luca Parmitano was out on a walk when water started filling his helmet. It leaked from the cooling system and pooled. Without gravity, the water clung to his face. He could not see. He could not breathe. It was creeping into his nose and mouth. He had to abort and scramble back. The leak did not stop the water, just kept building up as he struggled toward the hatch. By the time we finally stripped his helmet off, over a liter of water was floating inside. He came terrifyingly close to drowning in his own suit. It is a haunting reminder that space never forgives. One tiny failure, and I am in deep trouble. Even inside the station, our safety is incredibly precarious. My spacecraft keeps us pressurized, usually staying close to what you would feel at sea level back on Earth. It pumps in oxygen and scrubs out the carbon dioxide with complex systems while managing the temperature through active heating and cooling. It gives us some radiation shielding, but it isn't enough to stop every cosmic ray. And honestly, these ships are incredibly fragile. The hull is paper-thin, just a few millimeters of aluminum. It has to be that way to keep the launch weight manageable. Mass is our ultimate enemy. Every kilogram needs fuel. More mass means more fuel, and more fuel means even more fuel to lift itself. We call it the rocket equation, and it is merciless. The actual payload reaching orbit is just a tiny sliver of the total mass. On a typical rocket, only 3 to 5% of our launch mass actually reaches orbit. The rest is just fuel and structure we toss away. This means my home up here has to be incredibly light. Engineers shaved every gram they could, leaving us with thin walls and minimal support. Look at these walls. Most of the station is only 3 millimeters thick. That is barely 1/8 of an inch of metal. This thin aluminum skin holds our air pressure and blocks tiny dust specks, but it cannot do much more than that. This fragile hull is all that stands between me and the void. A single micrometeorite, screaming along at thousands of miles per hour, could puncture it instantly. We are constantly surrounded by clouds of debris and fragments from old satellites. At any moment, something could slam into us. Even a tiny paint flake is a deadly weapon at these speeds. Up here, kinetic energy grows exponentially with our velocity. We are moving at 4.85 miles per second. At that speed, even the smallest speck carries terrifying amounts of energy. A paint flake, just a few millimeters wide, hits like a high-powered bullet. It can shatter our windows or punch holes right through the metal. I see the damage every day. The station is covered in pits, craters, and deep scratches from years of these tiny impacts. We have been lucky so far, no major breaches. But it is a constant weight on my mind as we track every piece of junk out there. We sometimes fire the thrusters to dodge the big stuff. But you and I both know it is impossible to track every single threat. Anything smaller than 10 centimeters is invisible to our radar, yet it is still large enough to cause a catastrophic disaster. We live with the knowledge that an untracked pebble could pierce the hull at any second, causing our air to hiss out into the void. The odds are low, sure, but in the silence of space, low probability does not mean you are safe. It just means you are waiting. It means I am relying on luck. We have Whipple shields, layers of metal designed to break up impacts, but even they have their limits. When a small object hits the outer layer, it shatters. Those fragments spread out, hitting the next layer with just a bit less energy. These multiple layers are meant to slow the impact down. It works for the fast, tiny particles. But there is a breaking point. If something is too big or too fast, it is coming through everything. And we cannot just add more armor mass is our greatest enemy. More shielding means more weight, which makes it nearly impossible to launch. It is a terrifying trade-off between our safety and the cost. We just have to accept that some risk is unavoidable. My life support systems are complex. but they operate on the same basic rules as a suit. They keep me breathing, scrub the carbon dioxide from the air, and manage the heat and humidity inside this tin can. Up here, we recycle about 90% of our water. My sweat, the moisture in the air, and even my urine are all collected. Every drop goes through filters and purification until it is clean enough to drink. It sounds disgusting, but it is how we survive. Water is incredibly heavy. Launching it costs thousands of dollars per kilogram, so recycling every drop is way more practical than bringing more up. We drink that recycled water every single day. We always joke that today's coffee was really just yesterday's urine. It is the truth, but honestly, this water is cleaner than the tap water you have on Earth. The systems are that good. I get my oxygen from water through electrolysis. We run an electric current through it until it splits into hydrogen and the air I breathe. The oxygen keeps me alive. The hydrogen is either vented into the dark or combined with carbon dioxide to create even more water. We call this the Sabatier reaction. By mixing our exhaled carbon dioxide with hydrogen, we produce methane and usable water. We vent the methane overboard and electrolyze the water all over again. It is almost a perfect loop, minus a few tiny leaks. Air is always escaping through invisible gaps. Cargo ships bring us fresh supplies, but our recycling reduces what we need by 10 times. If I were heading to Mars, those systems would have to be even more perfect. There would be no resupply ships coming to save us. You would need to recycle 99% of everything, lose just a little bit too much, and you will never reach your destination. We can almost hit those levels now, but keeping a machine like that running for years in deep space is a nightmare. Things break. Filters clog. Sensors fail. Here on the station, I can just wait for a cargo ship to bring me a spare part. On a trip to Mars, you would have to bring every spare bolt yourself and pray that nothing breaks that you cannot fix. We also have to manage our waste. Every food wrapper, old package, and broken piece of gear adds up in our daily lives. On the station, we pack our trash into empty cargo ships. They undock and burn up in the atmosphere, vaporizing our garbage instantly. You cannot do that on a deep space mission. You would have to live with your trash for years or find a way to reuse it. Imagine the piles of plastic and broken electronics. A long mission could generate tons of waste. Where would you even put it? I cannot just throw it outside. It would become a hazard. We would have to store it in our living space or recycle it somehow. That is possible in theory, but it is incredibly complex and drains massive amounts of our precious power. You and I have to realize that no one has built a complete recycling system for all waste yet. It is a massive hurdle. We have to solve this before we go further. And then there is the heat. Managing temperature in space is its own kind of hell. You might think space is freezing, so keeping warm is the goal. For us, our biggest struggle is actually dumping heat. Our electronics, our bodies, every system humming it all generates heat in this vacuum. Out here, that heat can only be radiated away. We have these massive radiators, giant panels that bleed heat into the void. On the station, you can see them clearly in every photo. They actually glow faintly in infrared. If those radiators fail or take a hit, this whole station would start to overheat instantly. Temps would soar until our electronics shut down or just burst into flames. We'd have to bail. We almost lost it all in 2013. We have ammonia circulating through the lines, carrying all that heat from our living quarters out to the radiator panels. An ammonia leak means the cooling dies. We had to perform emergency spacewalks just to patch the leak and replace the pumps. It was a terrifyingly close call. Hours of grueling work in our suits, with several of us outside the airlock at once. The risk was much higher than a normal spacewalk, but we had to do it. Without cooling, this station becomes uninhabitable. We fixed it, but it showed us how fragile our life support is. Stick with me as we imagine this scaled for Mars. 6 to 9 months just to get there. Then, another stay on the surface, 6 more to get home, 3 years where everything must work. No resupply ships, no rescue team coming. If something breaks, we have to fix it using only the tools we brought with us. If we can't fix it, the mission is over. We probably die. This is why our mission planning has to be incredibly detailed. We analyze every possible failure. Redundancy is built in wherever we can fit it. 2 of every critical system, so if one fails, we have a backup. Spare parts and repair tools for anything that might break. We have detailed procedures for every glitch. Training is constant. so we know exactly how to handle any emergency that hits us. But you can't plan for everything. The unknown unknowns, failures no one expected, or problems that collide in ways you never imagined. Apollo 13 is our classic nightmare. An oxygen tank exploded right in the service module. It didn't happen during launch or re-entry, but during the routine cruise to the moon. A simple electrical fault caused a fire in the tank. The tank ruptured and oxygen vented into space. Suddenly, the power and life support systems for the entire service module were dead. The crew had to abandon the main ship and retreat to the lunar module. That's a tiny lander designed for short surface stays. They used it as a lifeboat for 3 people for 4 days, pushing their supplies way past the original design limits. They were rigging systems together in ways never intended, rationing their power and water while freezing in the deep cold. Carbon dioxide was building up because they didn't have enough filters. They had to jury-rig a solution using duct tape and spare materials to survive. It worked. They actually made it back and splashed down safely. All 3 survived, but it was incredibly close. Multiple times during that crisis, they were only hours away from running out of something critical: power, water, or even breathable air. They survived on skill, ingenuity, and luck. Out in deep space, far from Earth, an Apollo 13 scenario would easily be fatal. No quick return, and no mission control filled with engineers to save us. Communication delays would be measured in minutes or even hours. We would be completely on our own. This brings up another part of deep space missions that most people often overlook: the psychological challenges. Being trapped in a tiny spacecraft for years, knowing you are millions of miles away from your home, knowing that there is no rescue coming if things go sideways. The stress out here is absolutely immense. Even here on the station, where we can see our planet through the window and talk to family, the stress is a huge concern. We are carefully selected for our mental stability. We undergo extensive evaluations, and they provide us with psychological support during our missions. We have regular check-ins with psychologists on the ground. They schedule time for us to have recreation and personal activities. They watch our crew dynamics closely. Even so, we face challenges, conflicts between us, feelings of isolation, and sleep disturbances. We manage these issues, but they never go away. On a Mars mission, it would be worse. No more real-time conversations with family. You send a message and wait 20 minutes for a response. Everything becomes asynchronous communication out there. Emails, not phone calls. You watch Earth recede until it finally gets smaller and smaller. Eventually, it is just another star. Even the sun gets dimmer as we move outward. At Mars, sunlight is only 43% as intense. At Jupiter, it's 4%. At Saturn, it is only 1%. Beyond that, the sun is just a lonely star, cold and dark. This environment tests your sanity. Studies on Earth, analogues, where people spend months in isolation, show us that psychological stress is one of our biggest challenges. That includes interpersonal conflicts, losing your motivation, and struggling with the absolute monotony of life in a tin can. And those studies are on Earth, where they can leave if they need to, and help is always available for emergencies. In actual deep space, there is no leaving and no rescue. We are fully committed for the entire duration. If one of us snaps or falls into a deep depression, what happens? The rest of us have to manage it alone. I only have limited medical gear up here. Some psych meds, maybe a delayed chat with a doc on Earth. If one of us becomes a threat to the mission, our options are terrifyingly thin. Restraint or sedation are terrible choices, but they might be the only ones we have. It is the unspoken nightmare of long missions, the kind of challenge we rarely discuss aloud. Truth is, we don't know how a mind handles years out here in the void. The longest stint any of us has survived continuously is just about 14 months. Valery Polyakov set that record on Mir. 14 months, but he was still just in orbit. His mind held up, but a trip to Mars is a much longer haul. He could see Earth. He could talk to home. He knew help was just hours away. Deep space is different. The isolation is total. Some fear our minds will simply snap out here. Even for the best of us, this level of stress might be more than humans can take. Others say we will adapt, that with training we can survive years in the black. You and I won't know until we try. The first crew will be the ultimate test. They will face a hostile void and the crushing weight of being locked in a tin can. This thin metal hull is the only thing keeping the vacuum from taking my breath away. One tiny rock, a piece of junk, or a bad weld could rip us open. When the hull goes, my air rushes out instantly. In a bad breach, it's over in seconds. A small leak gives me minutes, but if I don't patch it fast, I am dead. That is why I have my suits and masks. Every protocol is written in someone's blood. I have patch kits for small holes, and I can seal off whole rooms to survive. If the failure is big, nothing helps. History is full of crews who ran out of air. Back in 1971, Soyuz 11 ended in a nightmare when a valve failed during descent. The ship opened up at high altitude. None of the crew were wearing their suits. They suffocated before they even hit the ground. Out here, space does not forgive a single mistake. One tiny valve, and 3 heroes were gone. We have changed everything because of them. Now I wear my suit for every launch. We check every system twice, then check again. But the danger is always there. Engineering can only protect me so much from the hostile void. Let's look further out together. Right now, I'm only 250 miles above the Earth. Up here, the planet's magnetic field is still shielding me from the worst of the radiation. I am mostly safe from solar flares and the heavy cosmic rays that haunt deep space. Ships bring me fresh food and water regularly, along with the parts I need for repairs. If things go wrong, I can be back on solid ground in just a few hours. But imagine going to Mars. It is a 6 to 9 month journey into the unknown. Out there, I'd be fully exposed. Every solar event would be a direct hit to my body. No turning back, no extra supplies. I have to carry every single thing I need to survive. My food, water, and tech must hold. My life support cannot fail for even 1 second. One failure is death. And the mental strain of this small cabin would be absolutely crushing. Watching Earth fade to a tiny dot while my signal takes longer and longer to reach home. When Mars is close, my voice takes 3 minutes just to reach the ears of mission control. That is 6 minutes for one hello. I ask a question and wait in the silence. At our furthest, it is 20 minutes each way. A 40-minute wait for a single reply. No live chats, no help from Earth. I have to solve every crisis on my own. The radiation is a silent killer. A round trip would spike my lifetime cancer risk significantly. We accept the risk as volunteers, but by any Earth standard, it is incredibly dangerous. Past Mars, the void only gets darker. You and I are seeing the start of space tourism, but for us out here, deep space remains a terrifying, beautiful frontier. I watch the worthy visitors arrive here at the station after paying tens of millions of dollars for their ticket. But these are brief, controlled trips. Participants must undergo intense medical screening and months of training. They are always with us professionals. Our spacecraft have massive safety systems, yet the risk remains ever present. Up here, every flight carries a danger you just cannot eliminate. Casual space travel for everyday people? That science fiction dream of routine spaceflight is nowhere near reality. Not for many decades at the very least. This environment is just too hostile. The engineering is brutal, and the costs are still astronomically high. For now, the void belongs to us, the trained pros, and the ultra-wealthy willing to gamble their lives. I often ask myself the big question, why come up here at all? Why send people into such a nightmare? Is the danger worth the exploration? You and I know our robotic missions can do most of the heavy lifting. Probes and rovers reach places I never could. They survive for decades in radiation that would kill me in minutes. We argue for human flight because we can adapt and make split-second decisions that robots just cannot handle. There is truth in that. But keeping me alive up here is incredibly expensive and terrifyingly complex. Every gram of food, every drop of water, and every breath of oxygen has to be launched from the surface. All that life support adds weight and cost. For most missions, my robot colleagues are just more practical. Usually, it comes down to inspiration. It is about the adventure and the symbol of humans exploring the great beyond. Those are valid, but they are not practical. They are about what we value and what gives our lives meaning. Then there is the big one, survival. Looking down at Earth, I know she will not last forever. Eventually, the sun will expand and swallow the inner planets. Thankfully, that is billions of years away. Our star is halfway through its life. It has about 5 billion years left before the hydrogen runs out. When that happens, it swells into a red giant. Our home planet will be consumed and vaporized in the heat. But long before that, Earth becomes unlivable. The sun gets 10% brighter every billion years. In about 1 billion years, the heat will be so intense that our oceans will simply start to evaporate. The water escapes into the void. Earth becomes a sterile, boiling rock. That is our natural, final fate. But we also have shorter-term catastrophes to consider, like a massive asteroid impact. A rock 6.2 miles wide, like the one that killed the dinosaurs, hits every 100 million years or so. The last one was 66 million years ago. We are not overdue, but it could happen at any moment. If a 6.2-mile asteroid hit us tomorrow, the consequences for the planet would be absolute. It would release the energy of billions of nukes, blocking out the sun and collapsing the entire food chain. Most large animals would die, likely including us. Civilization would crumble as the sky turns black. Billions would perish within months. We track the big ones, hoping for decades of warning to try a mission. We could try to slam a ship into it or use a nuclear blast to nudge the killer off course. We have never tested this for real, but the physics says it should work if we see it coming. It is the smaller rocks that worry me. They are hard to track and could hit us with zero warning. That is not an extinction event, but it could vaporize a city or cause tsunamis that kill millions. Then there are the supervolcanoes. Yellowstone is the most famous ticking time bomb on the surface. It erupts roughly every 600,000 years. The last one was 640,000 years ago. We might not be overdue, but a Yellowstone eruption would be a nightmare. Ash would bury North America. Gases would freeze the world, ruining crops and leaving billions to starve. Then there are the disasters we create. Nuclear war, pandemics, or runaway climate change. Even advanced artificial intelligence systems that decide we are the problem. From nanotech to global war, our civilization is fragile. Some risks are natural, others are ones we built ourselves. The reason for a spacefaring civilization is simple. Spreading to other worlds gives us a fighting chance. If something happens to Earth, humanity survives elsewhere. It is a long-term insurance policy for our species. Centuries or millennia are the timeline here. Building self-sufficient colonies on other worlds is monumentally difficult. Mars is our best bet. It is relatively close, and its day length is almost the same as Earth's. It has polar ice caps for water and an atmosphere we could eventually learn to process for survival. It holds the minerals for industry, but Mars is fundamentally hostile. Its air pressure is under 1% of what we have on Earth. The air is mostly toxic carbon dioxide. The cold is brutal, averaging -80 degrees Fahrenheit or -62 degrees Celsius. Summer at the equator might hit 70 degrees Fahrenheit, 20 degrees Celsius, but the poles stay locked in a deep, deadly freeze. Winter plunges to -200 degrees Fahrenheit, or -130 Celsius. Plus, the radiation out there is lethal. With no magnetic field to deflect cosmic rays, the atmosphere offers zero protection. Down on the surface, radiation doses are terrifyingly high. We are talking 250 times Earth's levels. To survive, you would have to hide away in shielded, underground habitats. You would bury your home under meters of regolith. Global dust storms can choke out the sun for months, killing your power. Visibility drops to absolute zero. Now, 38% gravity sounds manageable, but we honestly do not know the long-term cost. Long-term low gravity is a mystery. On the ISS, where I have been, zero gravity causes massive bone loss. You watch your muscles waste away. We exercise daily just to keep up, but we still return home weak with blurry vision. That comes from fluids shifting in your head. Your immune system glitches out, and it takes months to feel human again back on Earth. Maybe Martian gravity helps, but let's be real. Nobody has ever spent years living in partial gravity to see the actual damage. Perhaps that fraction of a G is enough to keep you healthy. Or perhaps it is not. It is a gamble. Years on that red dust would lead to brittle bones, withered muscles, and medical horrors we have not even imagined yet. We will not know until someone risks their life to try. Building a colony out there? That is a whole different beast. You would need to grow food in Martian dirt, but it lacks the life and microbes that make Earth's soil actually work. You would have to inject nutrients, recycle every drop of water, and keep greenhouses pressurized against the vacuum of space. The infrastructure is massive. You are mining ice to get water, then breaking it down just to have something to breathe. Energy is the bottleneck. Solar panels struggle because Mars is dim, and those dust storms can cut your power for months. Nuclear is the only real option, but that is a logistical nightmare. You need a full factory for parts and tools. We cannot just call for a resupply. Shipping costs are insane. Everything you need, you have to build right there on site. You need mines, refineries, and an army of specialists. Building an industrial world from nothing? That is a project for decades. Healthcare is another hurdle. People will get sick or hurt. There is no emergency evacuation back home once you are en route. A patient would die before the 6-month trip ended. Mars hospitals must handle everything from trauma surgery to bringing new life. Keeping doctors trained and supplies stocked is a nightmare. But then, you also have the human element, social and political stability. Put thousands in cramped, high-stress cans, and you have a recipe for disaster. Fights over food or power are almost inevitable. Space madness is real. Constant stress breeds violence. We would need rock-solid laws and serious mental health support just to survive. And that is on top of just staying alive. You have to keep the air fresh and the pressure seals tight. If the radiation shielding fails, everyone dies. One small system glitch can end the entire mission. That is the cold reality. This is not the old frontier. Mars demands high-tech life support every single second. One generation cannot build this kind of world. It would take centuries of help from Earth. Even then, success is never a given. The whole thing could still collapse. Gear breaks. Supplies vanish. One disaster could easily exceed what a small colony is capable of handling. Everyone dies, or the colony just barely hangs on, a ghost town in the making, never truly finding its feet. Constant dependence on Earth is not a future, it is just an expensive outpost. A real colony has to stand on its own. You have to survive if Earth goes dark. That is a massive bar to clear, and we are not even close to it. Past Mars, the nightmare only grows. The moons of Jupiter and Saturn, like Europa and Titan, are targets, but they are brutal. They have water, sure, but they are in the deep dark. Jupiter is 5 times farther from the Sun than Earth. Saturn is 10 times the distance. Sunlight is a joke out there, so solar is useless. You are strictly nuclear or nothing. The cold is unimaginable. Europa's surface sits at minus 270 degrees Fahrenheit, or minus 168 Celsius. Titan is no better. And Jupiter's radiation is a monster, trapping lethal particles in a massive, invisible cage around the moons. The surface would kill you in days. To survive, you would have to burrow deep under the rock or thick ice. The journey takes forever. It is 6 years to reach Jupiter, and 7 to get to Saturn. That is a long time in a tin can. Everything we fear about Mars is 10 times worse there. With our current tech, these worlds are simply out of reach. They are places to explore, not to live. But what about the ultimate void? Leaving our solar system behind? That means voyaging to other stars, facing the ultimate mystery of the deep cosmos. Out here, it is just me and a terrifying, hostile nothingness. Interstellar space is the freezing gap between stars. My nearest neighbor is Proxima Centauri, part of the Alpha Centauri system, 4.24 light-years away. That is about 25 trillion miles. If I were traveling as fast as Voyager 1, our quickest ship to leave home, my journey would last 70,000 years. It is impossible. I would need much faster engines to survive. Pulse propulsion, fusion rockets, antimatter drives, or laser light sails. Out here, these are just dreams on paper. We have studied them, but none exist. Even at 10% speed of light, which is optimistic, the trip would still take 42 years. We lack the technology. The energy I would need is just staggering. Speeding up my ship takes immense power. Bringing it to a halt at the destination takes even more. Chemical fuel is too heavy for me to carry. I need something far more efficient. Maybe nuclear fusion could work. Fusing hydrogen into helium to propel myself forward. My exhaust velocity could reach 10% of light speed, but I do not have a fusion rocket. We have barely squeezed energy from fusion in a lab back home. A fusion engine is decades away at best. And antimatter rockets? Those are even more of a fantasy right now. Annihilating matter and antimatter would give me perfect efficiency. The energy density is beyond anything I have ever seen, but making antimatter is incredibly hard. We have only created tiny sparks of it in our accelerators on Earth. It is not enough to fuel my ship. The price for an interstellar mission would be absolutely astronomical, costing more than the entire world economy. Then there are laser light sails. I could deploy a massive, thin sail. Lasers from Earth would blast the sail to push me forward. That way, I do not have to carry fuel. The power stays behind me on Earth. Calculations suggest that with a massive laser array pushing me and a light enough sail, a probe could reach 20% of light speed. Imagine that velocity. But the laser array would be massive, using hundreds of gigawatts. A system miles wide pointed right at me. My sail would be miles across but weigh only grams. It is technically possible, but the engineering is terrifying. It only works for robotic probes. You could never put a human like me on a sail that thin. I need life support, heavy shielding, and food. That adds weight, and more weight means I cannot move as fast. My trip gets longer, or I need more power. Then there is the stopping problem. Lasers can push me to speed, but how do I slow down? There is no laser at Proxima Centauri waiting to push back against my ship. I would have to carry heavy fuel to brake, making it harder to start. Or I just accept a flyby. I would scream past the star at high speed, take my readings, then drift into the void, never stopping. For a robot, that might be fine. For a human pilot like me, it is a death sentence. You cannot send me on a 40-year journey just to watch my destination zoom past. I need to land. I need to decelerate, which brings back the weight problem. Flying humans between stars just is not possible yet, not even close. Maybe one day, with fusion drives or antimatter and better life support, I could make it. The only thing out here is the background radiation, at about minus 454 degrees Fahrenheit. That is minus 270 degrees Celsius. My ship would have to generate every bit of its own power. I would need nuclear reactors, likely generators using the decay heat from plutonium to keep me alive. These can last for decades. Voyager 1 and 2 use them and still talk to us after 45 years. But they only give me hundreds of watts. Enough for sensors, but not enough to keep a human breathing. I would need megawatts of power. Huge reactors to run my life support, air recycling, and cabin heat. Launching that much radioactive fuel is dangerous. If the rocket explodes on the pad, it is a nightmare. Could I build one that runs for 40 years without breaking down in this weightless silence? Maybe, but it is not proven. Out here, the radiation is terrifying. No sun means no solar wind to protect me. I am exposed to everything. My ship would need meters of water or thick lead to keep me from frying. That is massive weight, which I cannot easily move. Or I just accept that I am taking a lethal dose. My cancer risk would skyrocket. Radiation sickness would hit me. It is a grim way to end a mission. At 10% light speed, it is still a 40-year trip to Proxima Centauri. That is my entire life. The pilot who launches will not be the one who arrives. I would be old or gone. It is a one-way trip. Imagine kids born out here in the black, living and dying in transit, having their own babies in the void. Sci-fi calls it a generation ship, but the reality is terrifying, keeping a closed ecosystem alive for centuries. Preventing inbreeding and keeping society from collapsing are massive hurdles. At least the original crew actually signed up for this. They made the choice, but their children were just born into this metal cage. Their grandchildren? They never had a say. How do I keep morale up when my crew has no choice but to finish a mission they never wanted? What if they want to quit? To turn back? 20 years into the journey, going home means another 20 years. Turning back is not an option. You are committed to the void whether you like it or not. A chilling nightmare. It forces us to ask about consent and the rights of souls born into a prison they cannot escape. Thinkers on Earth debate this. Is it truly right to start a journey knowing future generations have no choice but to stay? Is it worth it for the species? You and I do not have a clear answer to that yet. We must answer these questions before any mission launches, assuming we ever actually build the tech to pull it off. Long before we leave, some global catastrophe could make Earth completely uninhabitable. Asteroids, supervolcanoes, climate change, nuclear war, or engineered pandemics. All of them could end our civilization in a heartbeat. Spreading humans across different solar systems provides a backup plan. It gives our species real resilience. If Earth dies, humanity survives elsewhere. We are talking about thinking in terms of thousands of years. This long-term view actually makes perfect sense when you consider that our species could potentially survive for millions of years beyond today. From this height, survival is everything. Building the gear to survive hostile worlds and establishing permanent bases beyond Earth are the only ways forward. We are nowhere near that yet. The risks are staggering. Deep space is fundamentally trying to kill us. We evolved under very specific conditions. Pressure, temperature, and gravity define everything about who we are. We are tuned to Earth. My biology assumes those conditions will last. Take them away, and I just stop working. It is simple. We build tin cans and suits to mimic home. That is all a spacecraft really is. But these bubbles are fragile. One tech failure, and it is over. The universe is naturally hostile to us. That thin layer of air around Earth is the exception. Most of the universe is just freezing vacuum and radiation. Complex life cannot survive in most places. Maybe other beings evolved out there somewhere. Other worlds orbiting distant stars might have their own protective shields and atmospheres. They would be rare, lonely islands in a massive ocean of death, and the gaps are measured in light years. Reaching them would take tens of thousands of years. Entire generations would be born and die in transit. You would need a ship that acts as a perfect ecosystem. The engineering is far beyond what we can do. For now, space is just a place I can visit briefly with a massive support team behind me. I cannot survive here without constant help. It really puts into perspective how incredible our Earth actually is. That planet is home. Not just for my heart, but in a literal, biological sense. My body was built specifically for that world. Every cell in my system assumes Earth is there. We fit nowhere else in the universe. That makes Earth a precious, irreplaceable gem. It is the only place we know that naturally keeps us alive. We must protect it. Surviving here is harder than you realize. It is not impossible with tech, but it is a massive climb. We learn more every day, but solving these enormous challenges is going to take everything we have. Creating life support systems that run for decades without a single resupply mission is only the first step. We need radiation shielding that blocks cosmic rays without being too heavy. We need habitats that last for centuries. I have to worry about bone loss, muscle atrophy, and the crushing psychological stress of floating in a void. We would have to grow all our own food and recycle every drop of water. Nothing can be wasted. We need engines that can push us to other worlds in months, not decades. Maybe even faster than light travel, if physics allows it. This is engineering on a scale we have never seen. We might pull some of this off soon. Other parts could take centuries. You and I have to face it. Physics is clear. The deep void is a killer. Vacuum, radiation, extreme temperatures. Out here, willpower and optimism won't save my life. These are cold laws of physics. I cannot negotiate with a vacuum. I cannot reason with radiation. I either have the technology required to protect against these threats, or I don't. Without it, space is fatal. No one survives out here. Maybe 1 or 2 minutes, tops. The movies and the stories, they lie. They lie because the reality is far too harsh for drama. We do not float peacefully or freeze slowly. It is a violent, physical collapse. Consciousness gone in seconds, brain dead in minutes. No drama, just physics. I am not trying to be depressing, just real. Space is beautiful, awe-inspiring, and worth every study. From my view, the telescope images and distant worlds are profoundly interesting. The physics of the cosmos is stunning, but the danger out here is impossible to overstate. This environment is fundamentally incompatible with human life. Grasping this reality makes you respect the challenge. It helps you appreciate what we actually do up here. We are not just brave. We trust our lives to engineering, to spacecraft, and systems that must work perfectly. Otherwise, the consequences are immediate. Every spacewalk I take is a mission where failure means the total end. We do it because the risk is worth it. Exploration matters. Pushing boundaries and learning is absolutely essential. Extending our presence beyond the home world is worth the danger. But remember, out here, it is incredibly dangerous. Seriously dangerous. Not in some abstract sense, but in a visceral, end-you-in-seconds kind of way. Space doesn't care about my courage or my dreams. It only cares about pressure, temperature, and radiation. These laws do not bend for my needs. I either stay protected or I suffer the consequences. When you hear about missions to Mars or the outer solar system, remember the reality of what is actually involved. It is not like the movies. I am volunteering to spend months or years in a tiny, artificial environment. I am completely dependent on technology. Knowing a single failure is fatal. There is no quick rescue out here. It takes incredible engineering to keep me alive. Even then, I can never truly eliminate the risk. Even with the best tech and training, space is hostile. Deep space tests the very limits of human survival. It tests our ability to protect against the vacuum. And true interstellar space? That void is even worse. No sun means no heat, only the cosmic microwave background, just a few degrees above absolute zero. Cosmic rays with no shielding. We are so far away that communication with Earth would take years to reach. Out there, I would be truly alone. Light years from home, months from the nearest flickering star. If anything went wrong, there would be no help or rescue. We would have to solve it ourselves to survive. This is the reality. Space is unforgiving and indifferent to my survival. Yet, I still venture into it. We only venture out with massive technological support. Even then, it is brief. Casual interstellar travel is science fiction. It might become fact one day, but I'll need to solve challenges we are only beginning to understand. For now, Earth is our only home, the one place I can survive naturally within a thin shell of atmosphere, liquid water, oxygen, and stable temperatures. Looking from up here, I realize how rare these things are. It is all I have. Seeing how hostile deep space really is, that gives me a new perspective. It makes me love my planet more. I see the desperate need to protect Earth and its environment, because surviving without Earth's protection is far harder than you could ever imagine. Next time you look up, remember what is really there. Not just beauty, mystery, and endless possibilities, but vacuum, radiation, and extremes. A world that would end me in under 2 minutes if I'm exposed. Space is magnificent, but merciless. That is why I cannot survive without this extraordinary protection. It is not a lack of courage. My tech is limited by physics. It is the nature of the universe. Physics doesn't negotiate. Thank you for joining me on this journey. If this was valuable, please subscribe today. Help us keep examining the cosmos. Remember, Earth is special, a rare oasis in a truly hostile universe. The only home we have ever known. The only place I can survive without constant technical support. It is worth protecting and cherishing. We must understand its fragile, precious, and irreplaceable glory. Good night. Never take for granted that thin shell of atmosphere keeping you alive down there.